This is the 23rd video in a sequence on a course on single agent search. And in the last video, we introduced the idea of thinking about heuristics as coming from abstraction. We looked at Valtorta's theorem that said if we are trying to build a heuristic from an edge supergraph, that doing that at least at runtime is not going to be effective because the edge supergraph will require us to expand every state either in the supergraph or in the original problem. But what we saw was that if we generalize that, we could look at using an abstraction function. And by using an abstraction, that we would be able to get savings by expanding one state in the abstract graph, which corresponded to expanding many states in the actual problem. And so that's a review of what's in the last lecture. And we're going to take that in this video, and we're going to be looking at how we apply that in something called a pattern database. And we'll do this using what are called domain abstractions. So pattern databases. And we'll be looking at domain abstractions. And just to add to this discussion, a little bit of interesting history here. So pattern databases were invented in the mid-90s by at the University of Alberta by Joe Culbertson and Jonathan Schaefer. And they originally looked at this primarily in the sliding tile puzzle. And then in the mid to late 90s, I think it's 1997, the idea of a pattern database was applied for the first time to the Rubik's Cube. And it was actually applied very successfully to the Rubik's Cube. Rich Korf did that, and the work that he did there actually shed some insight, which we'll look at a little bit later, on what the impact of a heuristic is. But it was a big thing because that was the first time that random Rubik's Cube instances were able to be solved optimally. And so that's an important advancement to make there. And so we'll get a little bit into that, and we'll see some of the things that can be done. If you want to build a good Rubik's Cube solver, it's not nearly as hard today, well, as it would have been 20 years ago. Okay, so the idea, we want this abstraction, right? We want some sort of function phi. It's going to take a state and we're going to abstract it. And we might as well look at the sliding tile puzzle, but for right now, what we can do is we can write out the sliding tile puzzle as just, think about this 3 by 3 is just a sequence of numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8. And the idea here is I want to, so if that's going to be some s is equal to that, we'll call it s1, or actually it's the start state. And then what we want to do is apply a phi function, so phi of s1, and it's going to be a new state. And remember that this is surjective, we're mapping states down. So basically we want to map multiple states to a single state. And the way that we could be doing this, there's a number of different ways we could do this. So actually let's call this phi1. And for instance, in phi1, what I'm going to say is, let's get rid of all the odd numbers. So here I'm going to say, well, I'm going to do 0, and then I'm going to turn all the odd numbers into stars. So let's say 0 star, 2 star, 4 star, 6 star, and 8. Okay. And if we look at what's happening here, well, if we count the number of states that existed here, then there's 9 factorial possible states. And so we've got a state say, I mean, it's not too big from maybe a modern computing perspective, but we're going to reduce that to a smaller set of states. And what we see here is the first number is going to be able to go in 9 locations, and the next number in 8, and then in 7. And we have 1, 2, 3, 4, 5 numbers that we're going to be placing. So 9, 8, 7, 6, and then 5 locations. And so we can write this as 9 factorial over 4 factorial. Or just again, to write it, again, we've got 5 numbers here, so it's 9 factorial over 9 minus 5 factorial. So if I build a domain abstraction that abstracts, in this case, I have 9 elements. I take 5 of them and I abstract 5 of, I'm going to keep 5. I'm going to abstract 1, 2, 3, 4 of them away. Then my state space is actually going to be shrinking to be quite a bit smaller. In general, every variable that I extract away is basically one step in exponentially reducing the size of the state space. So what we see here is a domain abstraction like this by replacing some of these items here with just a general token here. And we could, of course, we could use two different tokens or other things like this. But when we do this, we're able to very quickly reduce the size of the state space. And if we think about in general, like if we're thinking about the sliding top puzzle, so we could have another abstraction here of S1, and we could just say, well, it's just the 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's 9 stars here, and I can just think about, well, I abstract away everything except the blank, and at this point there's only 9 possible locations that the blank could be here. So what we've done is we've taken a problem where we have an initial state representation. This is just one possible state, but for every state in the state space, we have some representation here, and then we have this rule where we're going to take values and we're going to replace them with other values, where the values we replace them with is going to be, it's going to reduce the set. So I don't want to somehow try and increase the value. It's surjective, so it's always a mapping down. So here, everything can go to star, and we've gone from 9 factorial to just 9 possible states in the abstract state space. And if we look at this, then what would the abstract state space be for phi 2? So we're going to map out what this is. Well, this is equivalent to this state space here that says, look, at the top, the blank is in the upper left-hand corner. And then we are going to have actions that we can take. I'm just not going to write out the stars to make things a little bit easier. But I could be moving the blank to the right, or I could move the blank down. And then the other thing that I can do here is I could be, again, moving the blank down or to the right. If I move it to the left, I'm going to go up in the state space. So I'm going to get something like this. Here's where I move the blank to the right again. Here is where I move the blank into the middle. And here is where I'm going to move the blank down. So there's the blank there. And then if we keep going, we get 2 more layers in this graph. And this abstract graph says now I'm going to move the blank right here. This one has me moving the blank right here. And the very last state I can get to would be saying the blank is in the bottom right-hand corner. Okay, so this phi function I have here, this abstracting a state space, it's mapping me into a state space with only 9 states, so 3, 4, 5, 6, 7, 8, 9. And what is the heuristic we're getting out here? The heuristic we would get out actually is essentially, if this is my goal state, essentially if I think about being at any state inside here, the heuristic I get is the distance from to move the blank to the goal. So all of these, just to be clear, all of these will have a heuristic value of 1, a heuristic value of 2, a heuristic value of 3, and a heuristic value of 4. Of course, this has a heuristic value of 0. But, and this is just done with a breadth first search, and I'll say a little bit more about that in a few minutes. But the idea here, so I apply an abstraction function, and I end up with an abstract state space. And I can do a search in that abstract state space, and I'm going to get this very small state space right here. And in this state space, then I'm going to get distances, in this case 0, 1, 2, 3, or 4, that represent distances in the true problem. Because you can see here clearly, if my blank is in the bottom right-hand corner, it's going to take 1, 2, 3, 4 moves, no matter how I do it, any path through here, to get to the blank to be in the upper left-hand corner. Now that may not solve the problem, and most of the time it won't, but there are instances where I could move the blank 4 moves from the bottom right and get to the upper left-hand corner. And so this is always going to be guaranteed to be an admissible heuristic. And this is exactly what a pattern database does. So we apply a domain abstraction, which basically applies a pattern to the representation of my state space, where we're going to remove some of the items that are here, replace them with some generic, a generic star or something like this. We don't actually keep anything in there. Like in my actual code implementations, I do put -1s in there as a way of distinguishing what's been abstracted. But the idea is that we have come up with some way of abstracting them away. And then I can get this abstract state space. And even if I didn't start with anything at all, what you should be able to see here, so imagine that I'm doing a breadth first search. So I give you a general problem and say, solve the sliding tile puzzle problem. And if I use a breadth first search, it might be very difficult to solve. But if I do a breadth first search in this state space, okay, so I'm going to go into this state space. I'm going to start from the goal state. I'm going to do a breadth first search backwards to reach every state inside here. I'm going to be doing 9 node expansions in that process. And I'm going to come up with this structure of the state space here. So this is going to be very inexpensive to do. As I said, only 9 states. And now what I'm going to do is I'm going to do a forward search from my arbitrary start state to this goal state right here. And the heuristic that I'm going to use are the values that are inside, that are stored here inside this graph. Okay, and when I do that, what we'll see here, I mean, what you'd see in general, is that this heuristic is at least somewhat more informative than a breadth first search. That is, there will be states here with that would normally, like normally I'd have a 0 heuristic everywhere, but knowing that the blank being in the bottom right hand corner is 4 steps away will actually eliminate many of these such states from consideration by the A* search. And the key here is that, well, there's 9 factorial states in the state space. There's 9 states in this abstract space. So each of one expansion here actually represents 8 factorial states. Okay, because there's 9 times that many. So each one of these represents 8 factorial states. 9 times that gives me the size of the full state space. And what that means is that when I do one expansion here by Val-Tortes theorem, by doing one expansion here, I'm actually satisfying the theoretical requests for many, in fact, up to 8 factorial states that might have been expanded in the actual state space now can be entirely avoided by doing this one computation here. Okay, so because this abstract state space is small, we can get usable information from it inexpensively, and we can use that information as a heuristic that will not only allow us to guide an A* search or an IDA* search or any other heuristic search, but not only will it be able to guide us to guide that search, but the cost of building the heuristic is has a good potential of having a payoff. Right, so it's not like an edge supergraph where I must expand everything; it will not have any payoff. Here, with this level of abstraction, I'm almost guaranteed to get some payoff. It won't be a big payoff. What there is there's a trade-off between the amount of abstraction that I apply and the amount of savings that I get. And of course, the more abstraction I apply, the cheaper it is to build my heuristic, but the less useful the heuristic is. And of course, if I just solve the original problem, then that doesn't help me at all. So there's this balance where basically as I get my heuristic stronger and stronger, these state spaces will stay fairly small. But you may want a slightly more complicated pattern here. And there's work, not recent work, but there's work from maybe 10 to 15 years ago, probably, that was looking at, for instance, could we build custom heuristics or do other things like this at runtime for solving problems. Now, as we mentioned in the last video, you could also pre-compute one of these and then solve many problems. And when you do that, then you're willing to pay maybe a much higher cost to do the pre-computation once and then reuse it for many problems. And so just to be clear here, because sometimes this process can be confusing, what does a search look like with a pattern database? Okay, so the first thing that I'm going to do, which it can be maybe offline, is I'm going to, or it could be done online, is I'm going to do a breadth first search from the goal. And the goal is actually going to be from phi of the goal. And in this, I'm going to compute the distance to the goal. Now, for simplicity here, we're going to assume, as we did a couple of videos ago, that we have unit edge costs and other things and like this. So unit edge costs Let's assume for simplicity there's no directed edges, although we could handle cases. I mean, both of these cases can be handled, but for simplicity here, we're going to assume that. So I do a breadth first search. It may be offline, and I'm going to get to the distance to the goal. So I build this graph here. And then what I'm going to do is I'm going to search with some sort of best first search. So it's a heuristic search algorithm. So that could be A star, it could be IDA star, it could be budgeted tree search, and whatever other algorithms I might want to apply there. And the key here is that now when I'm doing the search, I need to have a heuristic function. So I have some function heuristic, and it's going to take a heuristic between let's say, maybe not necessarily the start, but let's just say between some state A and the goal. And the question is, how do I compute this heuristic? Well, the goal here is implicitly already part of my heuristic because I've done the breadth first search from the goal and from the abstract state of the goal. So what I'm going to do here is I'm going to compute phi of A. So that's going to give me the abstract state, and then I want to look up the distance in my breadth first search of phi of A. Okay. In the next video, I'm going to talk about exactly the calculation that we do, and there's a number of different ways we can do this. So practically speaking, this is a numerical calculation that I'm using to index into a table, but we have to go through and describe how we build our heuristics. Sorry, we have to describe how we actually do this what this computation is, and how we can map these states into a table that's stored in memory. But in practice, there's a table in memory. This is going to give me a perfect hash function that is already going to take into account the abstraction here. And I'm just going to go into that table. I'm going to find a number in that table, and that number is what I'm going to return as my heuristic. But this could just be a general hash table. So I could just imagine putting these all in some sort of generic hash table data structure, and then I just, use my hash to look up what this exact state is and what the depth of that particular state is. But the idea is basically I do my heuristic computation, that abstract search, and then I just run whatever algorithm it is. But when I get to that algorithm and it says, give me a heuristic, well, I go look at the abstract state and I compute the distances within that abstract state. Okay. Now, there is a example of this in the sliding tile puzzle. There should be a link down below. It will take you there, and what you'll be able to see is a tree of the 3x2 sliding tile puzzle. You'll see some heuristics there. And so that's a place you can go and play with that. You can see how states are abstracted. I just want to make a couple points here that are useful for understanding what is going on here, or how we're doing this in practice. And so after we go through the mathematics, how we convert states and look them up and get their exact distances, I'm going to come back and look at what are some of the other things we can do when we do this computation. But in practice here, so let's just think about the sliding tile puzzle, and we'll use this as a concrete example. So if we have the sliding tile puzzle, what is actually going on here? So it ends up that Manhattan distance is a good heuristic. And you wouldn't want to just say, throw away Manhattan distance and use a pattern database instead. So for instance, for sliding tile puzzle, what you might do, or what we tend to do in practice, is we tend to say, look, I'm going to actually, if I think about the sliding tile puzzle, I can't afford, it would be solving the whole problem to just sort of enumerate the entire state space. So what we tend to do is say, well, look, I'm going to have, actually we tend to do it this way. I'm going to have one heuristic which uses all of these states right here. The blank is a special case, so we'll talk about that a little bit when we talk about some of the enhancements for this. But I tend to do something like this, and then I do something like this. I'm going to have a second pattern database, which is going to be this. So the blank is special because we need it to be able to move around. So we tend to keep the blank plus a bunch of other tiles. So in this case, this is the blank 1, 2, 3, 4, 5, 6, 7. And then this is the blank and 8 to 15. And so taken here, well, we can calculate the size of this. This is about 500 megabytes here, if I remember the math off the top of my head. And so Manhattan distance is a good heuristic. We might want to then say, hey, I want to add something like a heuristic like this or a heuristic like this to it. But the problem here is that this, when I try and do something like this, then what can happen here is that if I just can afford to put this, I'm actually not putting in my heuristic any of the interactions of the tiles at the bottom. So what we tend to do is take the maximum of, and then here, if I call this P1, P2, I'll often take the maximum of Manhattan distance, P1 and P2. And by doing that, I can basically say, look, for all the tiles interacting together, I get something about their distances. And then for getting these tiles to the goal, I know something about the cost of getting all these tiles. And for these tiles to the goal, I know something about the cost of those tiles. And I take the maximum of these is actually going to be admissible. Now, at least as we've described it. Now, it's possible to build this in a way that we can do better than the maximum. But again, we're going to cover that in a different video. But basically, if we have a baseline heuristic, we're going to want to combine that heuristic in. And we know that the max of 2 admissible heuristics is also admissible. And we also actually know that the max of 2 consistent heuristics is also consistent. So this is how you would practically apply this in the sliding tile puzzle, is you'd build 1, 2 heuristics plus Manhattan distance, and then you would take the maximum of all 3 of those heuristics to get the final heuristic for a particular state. And just to show here, what is the size of this? So this is 16 factorial, but I have 8 of these tiles that are not being used. So 16 minus 8 is 8 factorial. The size of this pattern database is 16 factorial. And now I'm using 9 of the tiles. So there's 16 minus 9 is 7 factorial that are not being used. And so 16 factorial divided by 7 factorial is... this is actually 4 trillion. But if you're able to get rid of the blank, and we'll talk about how we do that in practice, then this gets reduced to 500 million. And this one here starts out at 500 million and then compresses from there. So that goes from 500 million to about 50 million, or sorry, yeah, I'm looking at the net math here on my screen, to about 50 million entries. So this is 500 million. And we can actually get this down to 50 million if we are able to ignore the blank. And we have to do some special things to ignore the blank. And again, we'll talk about that in a later lecture. So typically when you see these used, we might use these 2 patterns, and then we would have a 500 megabyte plus a 50 megabyte. And this is a storage in my abstract state space. I'm basically ignoring all of these other tiles. I compute all distances of these remaining tiles. There's 4 trillion combinations, including the blank. Then usually I get rid of the blank on top of that. And I'm left with this combination here, which gives me a fairly good heuristic. And that will allow you to solve some very large, the standard test set of sliding tile puzzle problems very, very quickly. Okay, so this is the basic idea of using a pattern database heuristic, is that we are going to go and build an abstract state space, and we're only going to keep some portion of the state space. So down here we saw, like, here I'm keeping the bottom, here I'm keeping the top tiles. And then I'm going to go ahead and do an exhaustive breadth first search through that portion of the state space. And when I do that, then I'm left with, that gives me distances to all of those states. And I use those distances as heuristics in the actual state space. And I want to just look at one more last thing here. And that's the question of, why does this actually work in practice? Okay, so, so this is a PDB. And what we want to ask, this is an abstract analysis, but the question is, what heuristic value do we expect? Okay, and so the idea is we have a state space that is b to the d in size. So it's growing exponentially. And what we're going to do is we're going to abstract some number of states together. So in, like, if we look below, we choose some group. Maybe I'm just going to eliminate one tile from my state space. And so I'm going to get like a 10 times reduction in the state space or something like that. Well, what's going to happen is my state space that was b to the d, and actually let me write this more clearly, the maximum heuristic value that I get is representative of this sort of largest value. So b to the h is my old state space, where h is the heuristic value that I was able to get if I were to search, in fact, the entire state space. And this is going to be the heuristic value that I'm going to get in my abstract state space is going to be my actual state space, which has some depth d. And I'm going to take that state space, I'm going to shrink it by a factor of k. And the question is, what is the heuristic value that I get when I when I take my original state space, shrink it by a factor of k, and then do a breadth first search through that, assuming that the branching factor grows. So there's an assumption here that the branching factor is the same in the abstract and the regular state space. But if we look here, then what we can do is we just simply take the log of both sides. So we're going to get h log b is equal to, and then this gives us d log b. And then we get minus log of k, because that's what happens when we subtract. And what we notice here is, for instance, if I assume, we can really choose that this is any base. So let's just assume this is base b. Then what we have here, well, log b base b is equal to 1. So h is equal to d minus log base b of k. And so what this tells us is, if in my original state space, the distance across the state space was d, when I abstract the state space by a factor of k, I effectively subtract from the original diameter of the state space a log of this factor by which I divide. So what this says is I can divide by a very large factor, and the error I get in my heuristic is actually only a small value that's subtracted. It's the log of the amount that I divided by here. Now, it ends up, because the state space is growing exponentially, even a small amount of error introduces a large amount of extra states that have to be expanded. But it actually means that I can get a heuristic that is fairly accurate by dividing the entire state space by a factor of k. So I'm making the state space really small. I can afford to keep that state space in memory because I've made it so much smaller. And I don't lose quite as much on the heuristic. I don't lose very much on the heuristic because I only lose the log of that factor from my maximum heuristic value. So this is what a pattern database is doing, and this is actually why they're effective, is because I can shrink the state space exponentially, and I only reduce the heuristic value that I get by a much smaller amount, basically the log of the factor there. And so in other state spaces, we'll find that this isn't going to work, and we'll talk about that later in the class. But what we're going to do in the next video is we'll look at the mathematics of, like, how do I actually get this to work? We might have this abstract idea of, abstracting states, but what we do in practice to actually do this search, and what am I going to do to be able to do this mapping, to turn this into a table of numbers that I can actually use in a search. So we'll continue that in the next video.